So we'll begin now. Dear all, I'm Dr. Tulika Shah, and I welcome you all back to the second session of the Symposium on NLP for Social Good. We have our next keynote speaker, and it is with great enthusiasm that I welcome Professor Kevin Ashley, who is joining us online from USA. Professor Ashley is an expert in computer modeling of legal reasoning. He's currently serving as a full professor at the School of Law, a senior scientist at the Learning Research and Development Center, and a member of the Intelligent Systems Program of the University of Pittsburgh, USA. In today's keynote talk, Professor Ashley will speak on modeling case-based legal argument with text analytics, where he'll delve into the evolution of AI and law research, highlighting the transition from manual representation of legal knowledge to automated methods enabled by text analytics. With the recent advancement, particularly large language models and generative AI, have expanded capabilities in representing legal knowledge, but also raised questions about the role of argument models in the age of generative AI. Through the survey of some recent projects, Professor Ashley will aim to provide insights into the implications of these developments for the field of AI and law. Thank you, Professor Ashley, for gracing the event. Over to you.
Thank you very much. It's an honor to participate in this second symposium on NLP for social good. And everyone there in Liverpool, good afternoon. Here in Pittsburgh, it's still morning.
Yes, thank you.
AI and law has been the focus of my research for decades. It's a sub-area of AI where researchers build computational models of legal reasoning behaviors. I would like to tell you a story about how quickly technology is changing in the field of AI and law. But first, let me introduce these two areas in which I work. Case-based legal argument involves supporting legal inferences with arguments that compare a problem scenario with relevant cases. Over the years, my students and I have built computer programs that model this kind of analogical reasoning from precedents. More recently, I'm working in legal text analytics. It employs machine learning, natural language processing, and other computational techniques automatically to classify legal concepts or to predict outcomes in archives of legal texts, such as case decisions, contracts, or statutes. Now for my story of technological change. Here is a timeline of AI models of case-based legal reasoning since about 2017. I want to show you just how much has changed in the last 7 years. I will start with number 1, a particular knowledge-based model of case-based legal argument, and then move through text analytic approaches that apply machine learning to case text to predict outcomes, as in number 2, to predict outcomes and to classify issues and factors, number 3, and in number 4, to explain the predicted outcomes in terms of the issues and factors, and finally, that use generative AI to identify case factors automatically, as in number 5. In the first project, my student Matthias Grobmaier's VJAP program used a knowledge-based model of case-based argument. By knowledge-based, I mean a computational model in which aspects of legal knowledge, such as legal rules and concepts, are represented explicitly. VJAP stands for Value Judgment-Based Argumentative Prediction. One inputs a new case to VJAP, a current fact situation, or CFS on the far left, represented as a set of factors. Factors are another kind of legal knowledge. They are stereotypical fact patterns that strengthen or weaken a side's legal claim in a particular domain. VJAP uses argument schemes to analyze the case at bar based on relevant cases and precedents. Argument schemes are stereotypical patterns of legal argument. We'll see examples in a moment. VJAP uses the argument schemes to generate arguments, which it posts in an argument graph. Then it employs the argument graph to rank the arguments in terms of its confidence in the argument's outcomes. VJAP predicts an outcome for the input case based on the highest confidence arguments it could produce, and it explains its prediction in terms of those arguments. You can see an example of the kinds of arguments it generated in the middle. It draws analogical mappings from a target case to the most relevant precedents, where the analogies are drawn in terms of shared factors and the effects of a decision on the underlying values. Its arguments employed the explicitly represented legal knowledge, namely issues from the relevant legal rules, factors, and values underlying the legal rules, and issues which are all highlighted in red in that argument. And in an evaluation on the right, VJAP's highest predictive accuracy of 0.79 tied that of Naive Bayes, a machine learning model, but Naive Bayes could not explain its predictions. VJAP could. Now, VJAP is complex, and for purposes of this talk, I simply want to emphasize that VJAP contained a lot of explicitly represented legal knowledge. Its domain model included a set of logical rules governing claims for trade secret misappropriation and identifying the issues. These rules, which are represented by the rule tree in the center at the top, are based on the relevant statute and sources on the left. It included trade secret cases, represented in the center at the bottom, indexed by the issues and factors in green, and linked to underlying values at the upper right. It also included argument schemes for making and responding to case-based arguments, using the rules, cases, factors, and values in this domain model, as well as criteria for evaluating those arguments. By the way, VJAP is not unique. At the University of Liverpool, Professors Trevor Bench-Capin and Katie Atkinson, their students and associates, have constructed multiple successful knowledge-based computational models of case-based legal argument, including the Agatha and Angelic systems. Here is a more abstract view of such knowledge-based computational models of arguing with cases. As mentioned, the models employ argument schemes to represent patterns of legal argumentation. As I noted, the schemes are templates or blueprints for typical kinds of legal arguments. The schemes include, for example, arguing deductively from legal rules, arguing by analogy to past cases, or arguing from values underlying the legal rules. Other schemes address responding to such arguments, for example, by distinguishing a precedent or citing a trumping counterexample. One inputs the current fact situation. The argument schemes guide a search for a supporting argument or counterargument, and that is added to an argument graph. The process continues until there are no more arguments to add. Then the model evaluates the argument using legal proof standards and outputs a conclusion and the argument. So where is the legal knowledge? It resides in the legal reasoning domain model, which I showed in the previous slide, in the legal proof standards for evaluating the arguments, and in the argument schemes. Here are some examples of the argument schemes shown on the left that drove VJAP's reasoning process. They include schemes for arguing for and against outcomes based on their effects on underlying values, that is, on the value trade-offs. VJAP drew analogies to precedents in terms of these value trade-offs. Given a problem, VJAP generated a case argument graph shown schematically on the right. The graph comprised all the arguments that the program could make with all of the cases in its database using all of the argument schemes that applied. And now here are two important points about VJAP. First, knowledge-based approaches like VJAPs depend on manually representing the legal knowledge. Someone had to read the cases to represent the legal knowledge in a way that a computer could process. And second, factors were key. If factors could be identified automatically in a problem in cases, that's all that would be necessary to employ VJAP's ability to generate arguments with the rules, cases, values, and value effects. And we will return to that thought. Just 2 years later, however, the field moved dramatically away from these knowledge-based models to text analytic models based not on knowledge representation, but on statistical machine learning using a deep learning neural network. A picture may help to convey a simple intuition about deep learning neural networks trained on large databases of texts. Neural networks comprise input-output nodes connected to multiple layers of intermediary nodes via weighted edges. The inputs propagate through the nodes in the network to an output. The goal is to learn weights that minimize the difference between the computed output and the target output. Deep learning neural networks employ multiple layers. Hidden layers help learn features with predictive weight. Now here's the problem. Neural networks learn weights to make predictions about completing missing words, predicting what sentence comes next, or even predicting outcomes of cases. But they do not necessarily yield accessible explanations. The knowledge, such as it is, resides in the weights distributed across the network. It's difficult to tease that knowledge out of the network with which to fashion explanations. In addition, the weights do not necessarily correspond to the kinds of knowledge that legal professionals think is relevant. Indeed, the relevant knowledge for making an explanation may not even be in the network. The second point in my progression is a good example of this. Chalkidis's approach applied machine learning to case texts to predict outcomes. Chalkidis's neural networks worked directly from textual descriptions of a case's facts. Their models predicted if the European Court of Human Rights found a violation of any provisions of the European Convention on Human Rights, and of which provisions. Chalkidis's team trained and developed the networks with nearly 8,500 cases and tested it on 3,000 cases. By contrast, VJAP had only 121 cases. In terms of F1 scores, the weighted average of precision and recall, their BERT-based model predicted whether there was a violation with F1 equals 82%. It predicted which provisions were violated with F1 equals 60%. Those results were impressive. But Chalkidis's work also illustrated a limitation of legal text analytics. It could not explain its predictions in terms that legal professionals would understand. There are no legal rules or factors or values in this text analytic approach. Nothing with which to construct an argument or explanation that a lawyer would credit. What their machine learning could do is to highlight portions of text that influenced its prediction. It employed hierarchical attention networks, HANs, for this purpose. Hierarchical attention networks predict case outcomes and yield network attention weights. The figure at the left shows an HAN that computes attention weights for words at the bottom and then for sentences on top. HANs assign higher attention scores to the portions of text that have greater influence on the model's outcome prediction. Based on the HAN's weightings, an interface highlights the more predictive aspects of the text, as illustrated on the right. This led to a plausible idea. Can one use HAN highlighting to explain predictions and answers? Here, the model attends more highly to the words colored in various shades of pink and red and to the sentences indicated with the vertical heat bars. The subject here is Article 3 of the Human Rights Convention, which prohibits torture and inhuman or degrading treatment or punishment. And if you read the highlighted portions, they seem to be more or less relevant. But do they amount to an explanation? Carl Branting's experiments suggest that such highlighted, high-scoring portions of case texts do not amount to meaningful legal explanations. He engaged legal experts and non-experts on a task involving analyzing decisions of domain name disputes under the rules of the World Intellectual Property Organization, WIPO. WIPO has rules for resolving disputes about the use of internet domain names. For instance, such a dispute might occur where a cyber squatter registers and uses an internet domain name identical to or similar to a trademark or company name. Branting's user interface employed attention weight-based highlighting, that is, HANs. Each participant was asked to decide the issue of no rights or legitimate interests, NRLI, in two separate cases and to provide a justification for each prediction. No rights or legitimate interests is an important issue in WIPO domain name disputes. The participants saw highlighted case texts like the one above, where the most salient case facts are highlighted. Phrases highlighted in yellow favor the complainants. Phrases highlighted in red favor the respondents. For example, in the case at the right, to the left of the red arrow, the phrase "respondent submits that it has rights or legitimate interests" is highlighted in red. The results of the experiment suggested that highlighting neither helped nor hurt the accuracy of the participants' decisions. Branting observed, however, that the participants had difficulty understanding the connection between the highlighted text and the issue that they were supposed to decide. In other words, the highlighting indicates the phrase is important, but the participants did not necessarily understand why. Although one experiment is not determinative, this finding was a blow to hopes that HAN attention weights can explain legal predictions. Branting recommended that useful decision support should help the user understand the connection between relevant portions of the case record and the issues and reasoning of the case. Legal knowledge would be important in helping users understand this connection. But the question is, how can one integrate legal knowledge into this text analytic process? That leads to the third point of the progression, a promising research project described in Carl Branting's 2020 paper in the AI and Law Journal, Scalable and Explainable Legal Prediction. Branting's SCALE project applied machine learning to predict case outcomes and to identify issues and factors in the case texts, both of which could be useful for explaining predictions. The authors developed a semi-supervised approach called SCALE for annotating WIPO domain name disputes in terms of factual and legal findings. Text annotation involves marking up texts of case decisions to identify instances of semantic types of information. Types are the concepts of interest in the texts. For example, legal issues and the holdings in the cases. The types of interest are organized into a type system like the one you see here. It is a hierarchy of concepts and relations so that an annotation pipeline can learn to automatically assign the labels to new texts. The researchers annotated sentences from the findings sections of a small set of decisions in terms of the labels in this type system. The SCALE labels capture features keyed to the types of findings, issues, factors, and attributes that arise in the WIPO cases involving disputes about domain names. For example, see the issue of no rights or legitimate interests, NRLI, and its related factor for prior BIS use, both of which are highlighted in green. As I mentioned, no rights or legitimate interests, NRLI, is important. It comes from one of the WIPO rules governing domain name disputes. That rule states the importance of a bona fide business use of the domain name prior to notice of the dispute. Here are samples of annotated text excerpts from the factual and legal findings sections of 2 domain name dispute cases. Human annotators assigned the labels shown in the last column under the red arrow. These labels come from the SCALE type system that we saw in the previous slide. The researchers bootstrapped their small set of manually annotated instances so that the model could label the sentences in the finding sections of all the cases in the WIPO corpus. They confirmed that the projected label annotations predicted case outcomes with reasonably high F1 scores. And as a bonus, the tags represented substantive conceptual features that could be used to explain the predictions. For example, the text to the right of the blue arrow says, the respondent clearly is not making any non-commercial or fair use of these domain names. That text in a case might end up being highlighted as having weight, but now that text will be associated with an annotation to the left of the green arrow that relates it to the issue of no rights or legitimate interests as a legal finding. With that kind of labeling, the highlighted portion of text could then help human users to make a connection to the legal task they were meant to perform. SCALE's predictions were accurate, but the SCALE program stopped short of actually explaining them. In addition, as Branting points out, WIPO cases have a high degree of stylistic consistency in the language used in the findings sections. It was an empirical issue how well these techniques would apply to legal domains with more complex and varied scenarios. And that brings us to the 4th project on the timeline, applying machine learning to case texts to predict outcomes by classifying issues and factors and explaining the predicted outcomes in terms of the issues and factors. This is work of my current student, Morgan Gray, in the DIAZ project. His program learns to identify factors in case texts, to use the factors in predicting case outcomes, and to explain those predictions. We're working with drug interdiction automobile stop cases, DIAS cases for short. In the United States, police officers regularly stop motorists for minor traffic violations and sometimes end up searching the car for drugs. The legality of the search depends on whether the officer's suspicion was reasonable. If not, the evidence resulting from the search can be suppressed. We identified a set of substantive factors that courts used in determining if a police officer has reasonable suspicion that an automobile contains illicit drugs. These factors of suspicion are listed on the left. They have to do with the appearance or behavior of the vehicle's occupants, the occupant's status and travel plans, and the vehicle's status. This is our type system. Law students manually annotated the sentences in 211 DIAS cases in terms of factors of suspicion. Morgan trained a supervised machine learning model, a fine-tuned Roberta language model, to automatically annotate sentences by factors. Table 3 on the left shows the results of his test. Where there were 10 or more sentences to train from, the F1 scores ranged from 70 to 92%, which is pretty good performance. In a second experiment, we tested how well various machine learning models could predict and explain case outcomes based on the identified factors of suspicion. We applied the machine learning models shown in Table 4 at the right to predict the outcomes of the cases in the test set, and where possible to identify the most important factors for the prediction. All the models tested outperformed the two baseline models. The best performing models, the neural network and the random forest models, achieved 97% accuracy. These results show that at least with our 211 cases, the factors of suspicion in our list can accurately predict the outcome of suspicion, reasonable suspicion. Now let's look briefly at the decision tree model underlined in green and the K nearest neighbor model underlined in red. The decision tree model shows which of the factors can be used to predict the case outcomes most efficiently. At the root node, the model asks whether factor 4n is present in the input case. This factor, unusual vehicle ownership, has to do with whether the car is rented or otherwise owned by a third party. If 4n is present, the left branch is followed and we reach a terminal node. The model predicts that a reasonable suspicion is found with a probability of 78.78. If 4n is not present, the right branch is followed and the process repeats with a new factor, 1d, suspicious or inconsistent answers. We found that with just 4 factors of suspicion, the model can explain all of the case outcomes with 80% accuracy. This kind of analysis raises interesting policy questions. After all, millions of people rent automobiles. Should renting an automobile be that important from a normative viewpoint, given the risks associated with auto stops? Of course, here we're only dealing with 211 cases, but with the ability to apply text analytics to identify factors automatically in the cases, we can process many more cases and strengthen our conclusions about this legal domain. Since the publication of the paper, we're now up to some 500 cases. Now let's turn to the K nearest neighbor model. One can use k-nearest neighbor to identify the cases that are most similar to the current fact situation. Here we show a current fact situation on the left with its factors listed in blue. Our decision tree algorithm has predicted an outcome of suspicion found. The two most similar cases are shown in red at the right. The most similar cases are the ones that maximize shared factors and minimize unshared ones. Comparing them to the current fact situation can lead to a better understanding of what the outcome depends on. Here, one can see that the outcomes of these two cases also were suspicion found. This tends to confirm the predicted outcome of the current fact situation. Sometimes, however, the most similar cases might have the opposite outcome, which might reduce one's confidence in a prediction. One can compare these neighboring cases to determine if they have factors whose presence or absence makes a difference in the current fact situation. This kind of explanation with nearest neighbor cases is not quite a case-based argument a la VJAP, but it's a step in that direction. In other words, we're starting to use machine learning automatically to fill in the legal knowledge, including factors that a knowledge-based computational model of case-based legal argument could employ, and that could help to explain the machine learning program's outputs. By the way, Katie Atkinson and Jack Mumford are pursuing similar efforts with their Angelic system at the University of Liverpool. Now let's turn to generative AI. One of the most effective text analytic methods to date. As you know, generative AI involves deep learning neural network models that can be trained on vast amounts of data and that can then generate new examples from scratch using patterns in that data. For example, a language model such as GPT-3 or GPT-4 can be trained on large amounts of text data and then used to generate new, coherent, and grammatically correct text in different languages, both in terms of input and output, as well as extracting relevant features from text, such as keywords, topics, or full summaries. For these generative models, the user inputs prompts to the systems. The prompts control the system's outputs. Well-defined prompts are the recipe for a successful conversation that covers the topics of interest. The generative models may support zero-shot, one-shot, or few-shot learning. These indicate if a prompt provides no examples, one example, or two or more examples of a targeted response. Perhaps the most interesting feature of generative AI is that the systems can understand and follow instructions in the prompts written in natural language. This is a result of their having been trained via reinforcement learning. And with that, we come to the fifth project on the timeline. Morgan Gray has applied generative AI, that is GPT 4.0, to identify factors in case texts automatically. Gray employed few-shot learning with prompts like the one on the left to label factors in Diaz cases. Interestingly, the prompts are based on the same instructions that we provided to human annotators when they performed manual annotation. GPT-4 can understand those instructions. Morgan showed that GPT's annotations substantially agreed with a set of manually annotated gold standard cases, as shown in Table 5 at the right. Table 6 at the lower right shows that GPT-4 also achieved high agreement with the gold standard and the law student annotated sentences as to which sentences were factor-like. These are sentences that look like they may contain factors. These results, I think, are important. Using GPT-4 to pre-annotate factor sentences or factor-like sentences could make human annotation more effective and efficient. It could direct the annotators to the sentences that are most likely to contain factors, and then they can exercise their human judgments. We do think it's important to keep humans in the loop in this kind of annotation process. We have seen some ways that legal knowledge for case-based argument can be represented when using text analytic approaches. As you can see from this progression, a lot has changed in just 7 or so years. Where is this progression leading us, especially in an age of generative AI? I suggest that the answer may be argument scheme-based prompting. Let's call it the 6th point on the progression. As we have seen, one needs to prompt GPT-4 to predict a label or to answer a question. Today, we are seeing examples of structured prompts in the legal domain. Some of these prompts are shown here. A prompt to lead GPT to reason through a legal syllogism. Prompts to assess whether a hypothesis is legally entailed in a situation, and a prompt to rate the best case-based explanation of a statutory term. Structured prompts like these look increasingly like argument schemes. Recall that argument schemes are templates or blueprints for typical kinds of legal arguments. I think that argument schemes and domain models like those in VJAP, Scale, and the Diaz projects could provide the concepts to use in prompting and guide the structure of the prompts. In my lab, we are experimenting now with generating prompts for generative AI to perform case-based argument tasks, such as drawing legally relevant analogies across cases, distinguishing one case from another, reasoning about the effects of a case decision on underlying values, or posing a hypothetical scenario to test a proposed rule. We have generated some promising results, but we have more work to do. There are open questions, however. Can prompting make explicit enough implicit knowledge about case-based legal argument? Not only are there technical constraints on the lengths of texts and prompts, although these are being liberalized recently, but the cost of using OpenAI's GPT models is an important limiting factor. In addition, OpenAI's GPT is a black box. We don't know on what legal documents OpenAI's GPT models have been trained. We don't know the extent to which they can generalize from that training set. Such limitations are leading researchers to turn to smaller open source LLMs like Llama or Mistral that they can run locally and train with their own sets of documents. Will argument scheme-based prompting generalize? Can it lead to creative arguments? Argument schemes apply across different legal domains, but the domain models do not. We haven't seen examples of factor-based arguments in, say, one legal domain leading a program to make analogical arguments in another. A bright spot for that kind of creative argumentation is that prompting employs natural language, and I suspect natural language can generalize more easily than knowledge-based representations. We should focus on the relationships in a domain model among the issues, factors, and values. These relationships may generalize more effectively across different legal domains, especially if the domains are somewhat related. For example, these relationships in the Diaz autostop domain may map onto other criminal law contexts where reasonable suspicion or probable cause is important. Finally, there's the question of whether argument scheme-based prompting is even necessary. Could it be that given enough examples of case-based legal argumentation in legal opinions, briefs, and similar texts, could it be that an ability to make such arguments would emerge automatically, a kind of emergent property of the documents? I doubt it. The VJAP example shows how much knowledge is required, and that probably is just a small fraction. But today, in another 7 years, who knows? Let me end with these takeaways. Large transformer language models like GPT-4 can supplement and supplant manual annotation of case texts. Automatically identifying legally relevant factors in case texts and using factors to analyze and explain legal outcomes are feasible. Knowledge-based computational models of legal argument, like VJAP and those developed there in Liverpool, can help explain and critique machine learning predictions. And argument schemes and domain models, like those in the VJAP, Scale, and Diaz projects, could inform argument scheme-based prompts to strong LLMs to generate case-based legal arguments. And with that, I'm happy to answer questions.
Thank you, Professor Ashley, for an interesting talk. We'll now take up questions from both the virtual and in-person attendees. For virtual attendees, please drop your question in the chat box. And for the in-person attendees, do you have a question? Anyone? Yeah, please, Projata, you can come in.
Hi, Professor Ashley. So I had one small question regarding this K-NIN-based similarity where you were explaining, I think in slide number 17. So where you were explaining that using K-nearest neighbors, you are
Yes.
trying to do the prediction. So I just wanted to know that how this nearest neighbor similarity was computed between the, yes, this one. So when you say this rank 1 case, rank 2 case, so how this similarity is computed? This similarity is on the whole text or like based on the factors or something like that?
It's based on the factors. It's based on sets of factors. And we just use a nearest neighbor algorithm. I'm not sure which.
Yeah, that is, yeah, I just wanted to know like how the documents are represented. So it was based on the factors.
That's
Okay.
right.
Okay.
That's right.
Yeah, and like I have this follow-up question on that. So I mean, do you think like in like modern text analytics, we have a lot of kind of good representation algorithms in NLP, like text embedding, we can get a dense vector corresponding to a large text and all. So how those kind of, using that kind of embedding representations also we can compute the similarity between the two legal cases and all, and then compute this nearest neighbor. So, I mean, can you comment on this, like whether this kind of factor-based similarity is more kind of reliable compared to that kind of using this whole dense representation of text, like where you just give as input the whole legal document and then compute the similarity based on that whole textual content. So, yeah.
So as to reliability, that's an empirical question. And I'd be interested in the experiments that resolve that. but I'm not so much focusing here on reliability as explainability. The factors are concepts that are employed in the legal domain, in this particular legal domain. Other factors are applied in other legal domains, and lawyers understand the kinds of arguments that are made with them. And thus, I think it's important to make that connection between and to identify the sorts of features in the cases that do allow attorneys to make the connection to the legal rules that they need to apply.
Okay, thank you.
Any other questions from the in-person attendees? No? Do we have something from the virtual attendees? No. Professor Ashley, I have a question. So,
Yes.
So you said in the last work that you're using large language models, for example, GPT-4, prompt them to, give reasoning behind the hypothesis, right? So we all know these large language models are biased related to some attributes, some aspects. Do you think these inherent biases in these LLMs affect the generation capabilities of the reasoning and arguments when we do prompting in a constrained manner, given the premises and the hypothesis in the legal domain?
I think that's a problem that I am eager to investigate. In the United States, these drug interdiction auto stop cases are often focused on Black drivers. And the auto stops have led to violent altercations with drivers, understandably. In fact, in the earlier 2010 era, scholars came to refer to this as dealing with the crime of driving while Black. So race is definitely a potential confound in these cases, if you will. And we're I've been trying to, we've made some efforts, and I'm trying to get some funding to continue the work to identify instances of racial bias in the cases. And if we can do that and also compute the factors and their weights, we are in a position to compare decisions from different regions of the United States where one might expect the racial differences could affect the weights and introduce an element of bias. We could compare decisions at the trial court level with the appeals court level. We would be able to do some interesting analysis that has policy implications. Interestingly, in the United States, a number of jurisdictions are deciding as a policy matter that these sorts of stops should be prohibited completely. And so we would be in a position of providing some evidence that could affect those policy decisions.
Right. Thank you for your answer. I think we have no more questions from both virtual and in-person attendees. I would like to thank you, Professor Ashley, for your time and support for this event and for delivering such a wonderful talk. Thank you very much.
Thank you very much. Thanks for inviting me. Bye-bye.
We have a break now for 15 minutes, and we'll be back for a paper presentation followed by an invited talk.